This is the first video in a series that I'm making to support a course in complex analysis taught at around the junior or senior, in other words, the third or fourth year undergraduate level. So we're going to start pretty basic, and that is with the definition of a complex number and the set of all complex numbers. So a complex number is any number of the form a plus bi, where a and b are both real numbers, and I is the special imaginary number so that when you square it, you get -1. You can think about I as a square root of -1. Now we can group all of these objects together into something called the set of all complex numbers, which we will denote by this blackboard bold C. So again, that's just a plus bi as a and b range over all real numbers. So obviously we could write down just some trivial examples of complex numbers pretty easily, like the number I is a complex number, so is the number 2, so is the number pi, so is the number 3 minus 7i. Those are all like pretty basic examples of complex numbers, given that they satisfy this kind of construction rule. Okay. So a nice visualization tool of the complex numbers is to be visualized as a complex plane. You can maybe think about this as the real plane, R2, in other words, R cross R, with some extra structure. So here we've got the real axis. So I've just said this is R. So like it said, it's the real axis, and then the imaginary axis. So on this axis, everything is a pure imaginary number. In other words, it's a real number times I. So if we've got an arbitrary number in C, we can write it as a plus bi, like we said over here. But that corresponds to this point in the complex plane. So notice it's a units along the real axis, and then b units along the imaginary axis. But notice, like I said before, being on the imaginary axis means you are of the form b times I. Okay, so now let's look ahead real quick to see where we might go before we look at some basic operations. Well, one of the things that you do with just R2, in other words, the Cartesian coordinate plane, is you look at different coordinate systems under this plane. And so this, you can do the same sort of thing with the complex plane. Here we have like a rectangular view of these numbers. So in the next video, we'll look at a polar view of these numbers. So it's pretty obvious to think about the distance from the origin to this number a plus bi, which we'll see what that distance is later in this video, as well as the angle that this ray makes with the positive real axis. That's also something pretty interesting as well. So maybe like next time we should say the polar form. But in this video, we're just going to mostly or always deal with the rectangular form of a complex number. Okay, so now that we've got these basic definitions out of the way, I want to look at some unary and binary operations that can be done on the complex numbers. So far, we've built up the basic definition of the complex numbers. Now we're ready to look at some unary operations and binary operations on the complex numbers, in other words, on C. And by unary operations, I mean they are operations that you do to a single complex number. And a binary operation would be one that you do to a pair of complex numbers. So we're going to use the standard notation by calling an arbitrary complex number z. Later that will play the role of a complex variable, but we're not there yet. And so z is equal to our complex number a plus bi. And here we want to look at 4 unary operations. So the first two are fairly straightforward, and that's the real part and the imaginary part. So here, the real part of z, well, you can probably guess just by the name. That's just going to be, well, the real part. So in this case, it would be a, because z is equal to a plus bi. Okay, now what's the imaginary part? There might be a little bit of a question here. Is it b or is it bi? But it's really just b. So in other words, the coefficient of our imaginary number I in the expansion of z. Okay, so there's real part and imaginary part. I don't think we need to say so much about that. Now let's move to the complex conjugate. So we denote that with an overline. So here we'll say z bar, and that's how we'll read it. So if z is a plus bi, then z bar is a minus bi. Okay, there's actually some nice geometry that goes along with this. So let's get a complex plane on the board, and let's say that z is right here. Well, now what will z bar be? Well, notice it has the same real part, but the imaginary part has been negated. So that represents some sort of folding by the real axis. So z bar would be down there. So notice what we did is we kept the same distance from the origin. And we also, in turn, kept the same real part, but we have negated the imaginary part. So if this were a here, then this point over here would be bi. This point over here would be negative bi. Great. And if you're looking ahead, these angles would be the same. Now, depending on how you're measuring, you might think of this as theta and this one as minus theta. But that's kind of getting ahead of ourselves. Okay, so now let's look at the modulus. So I'm going to write the definition, and then I'll motivate the definition. So the modulus of z, which is defined by this kind of absolute value symbol, although we use the word modulus when it has to do with complex numbers, that will be equal to the square root of a squared plus b squared. Okay, so now let's get another copy of the complex plane on the board so that we can figure out what that means geometrically. And this is going to be a common thing going back to the geometry of these operations. You could cook up some geometry of these two operations, but these are maybe a little too simple to really worry about at the moment. Okay, so let's go over here. Let's say we have our point A plus BI, so that's about right there. And let's notice that we can put a triangle in the plane built out of this complex number. So there's the triangle in the plane. Notice that this guy down here has length A. That's the distance from the origin. This guy right here has length B. Now we're just measuring that distance there. We're in the first quadrant, so we don't have to worry about changing the sign here. But then by the Pythagorean theorem, this guy right here has length square root of a squared plus b squared. So you can think about this as the length of the hypotenuse of the completed triangle of our complex number z, or as the distance of z from the origin, which is essentially what's going on here. So notice if this point right here is z, then the distance from the origin is this measurement here, which we called the modulus of z. Okay, so now we've got our unary operations on C. Let's get rid of this and we'll look at some binary operations on C. So now we're ready to look at binary operations on C. That means we need two complex numbers. So generally, if you call one of them Z, it's standard to call the other one W, unless you want a subscript, but let's just keep it Z and W here. So here I've set Z equal to A plus BI, just like we had before, and W is equal to C plus DI. So the two binary operations we want to look at are addition and multiplication. And so let's start with addition. You can probably guess how to define both of these operations, as it's pretty straightforward given this definition of I squared being minus 1. So if we have Z equal to that and W equal to that, then Z plus W will be A plus C plus B plus D times I. So in other words, you just add the real parts, and that's the new real part. You add the imaginary parts, and that's the new imaginary part. But something really interesting is happening if you look at this geometrically. So let's say we've got our complex number Z right here. So we can just write that as the ray from the origin, ending at Z, starting at the origin, like I said. Let's say here is W. So what is Z plus W in this case? Well, if you know anything about adding vectors, which is kind of essentially what's going on here, you will know that addition of vectors is like completing a parallelogram. So here we can complete a parallelogram here, here, and this is going to be the point Z plus W. So if I did a good job here, this top line would be parallel to this line segment, and so on and so forth there and there. So if we were to put this together, This line going from here to here represents this z plus w. So now that we've got this taken care of, let's maybe look at multiplication. Okay, so now that we've looked at addition of complex numbers, we're ready to look at multiplication. You can probably guess how this goes. So given z and w defined like we had before, I'm going to write out some details here. So we have a plus bi, c plus di, and now we're just going to FOIL it out, keeping in mind that I squared is -1. So there we'll have a times c plus a times d times I plus b times c times I, and then plus b times d I squared, but that I squared is a -1, so that changes that plus into a minus. Now we can group real and imaginary parts, and we see that this is AC minus BD, and then plus AD plus BC times I. So there's our product looking at the real and imaginary parts. We're not quite just yet going to look at the geometric implications of multiplication by complex numbers, because we really need to talk about the polar form, which we will do in the next video in order to investigate that geometry. Okay, so now that we've looked at a couple of operations, now let's prove some very basic results involving the arithmetic of complex numbers. Now we're ready to look at some propositions involving the arithmetic of complex numbers. So let's see, I've got 7 of these basic results on the board. I'll prove a couple of them and leave the rest of them as like warm-up exercises. So let's look at this first one. It says that the modulus of z is equal to the square root of z times z bar. So let's maybe just check that. So let's check the square root of z times z bar. Maybe throughout, let's set z equal to a plus bi, and we'll set w equal to c plus di, kind of just like we did before. Okay, so that means we're going to have the square root of a plus bi times a minus bi. But notice that's going to multiply out to a difference of squares scenario. We'll have a squared minus b squared I squared, but that I squared will change the plus to a minus. So this gives us the square root of a squared plus b squared, which is exactly equal to the modulus of z. Okay, so that's good. That means we've proved this first result. Now let's move on to maybe this second one, and that is 1 over z is equal to z bar over the modulus of z squared. So that actually follows from this pretty quickly. So how do we do that? Well, let's notice that z times z bar over the modulus of z squared is exactly equal to the modulus of z squared over the modulus of z, which is equal to 1. But now from this equation, we can just divide both sides by z. Here, I guess I should point out that we're assuming that z is non-zero. But dividing both sides by z, keeping in mind this and this portion of the equation, we get our result. So I'll just put a check mark there. Okay, good. So that means we've proven this second result. Now let's move on to this third one, proving that the real part of z is the modulus of the real part of z, which is actually just the absolute value of the real part, given that that's a real number, is less than the modulus of z. Okay, so let's notice that the absolute value of the real part of z is exactly the absolute value of a, but that's exactly the square root of a squared. Okay, but now that's less than the square root of a squared plus b squared. I guess I should have a less than or equal to there because the imaginary part of z could be 0. Okay, but now that's exactly the modulus of z by the definition. So we've completed that inequality. Okay, so that's looking good. Now let's maybe move on to this one, then we'll clean up the board and do the multiplication problem, and that's it. So let's maybe start with this right-hand side. We have 1/2 z plus z bar. Let's notice that that is half a plus bi plus a minus bi by the definition of z and z bar, but that collapses to 1/2 times 2a, which is just the real part of z as needed. Okay, so we've proven this part as well. Okay, so let's get rid of this portion of the board and we'll prove this one as our final proof. These two will be left as homework exercises. Okay, so like I said, we're gonna finish it off with this last result. Again, z and w are defined as they were before. Okay, so let's notice that z w bar, in other words, we're taking the product first and then the complex conjugate, that's equal to, well, let's just recall that z times w was ac minus bd plus I times ad plus bc. Then we need to bar that. Okay, good. But now let's notice that that is exactly equal to AC minus BD minus I times AD plus BC. Okay, good. Now let's see what we get for the other. So here we'll have Z bar times W bar, but that's A minus BI times C minus DI, just by the definition of the complex conjugate each time. But that simplifies out to A times C. That's this A times C. Then the minus signs cancel when we're multiplying B and D. But we get another minus sign from the I squared, so that'll be minus BD. Okay. And then notice we'll get exactly this. So we'll have minus I AD plus BC, just multiplying this out. So that completes this equality here. Okay, so we've proven this last one. Like I said, these two will be homework. Okay, so let's get rid of this and then we're gonna look at something called the triangle inequality. Okay, so as promised, now we're gonna look at something called the triangle inequality. And that says for all complex numbers z and w, the modulus of z plus w is less than or equal to the modulus of z plus the modulus of w. Okay, so let's get started. So instead of proving this inequality, we will prove the inequality where we square both sides of this inequality. Notice since these are positive real numbers, the square function will give us exactly what we want. Okay, so that being said, we've got the modulus of z plus w squared. That'll be the thing that we work with. So by our last proposition, we know that that is exactly equal to z plus w times z plus w bar. But I can distribute that bar over the z and the w. Now multiplying this out, I get z times z bar, which is the modulus of z squared. And then I'll have z times w bar plus z bar times w plus w times w bar, which is the modulus of w squared. So that's what I get from multiplying that out. But now let's notice that this guy right here, this z bar times w, is exactly the same thing as z w bar bar. But that means that we can take these two objects, this guy, and add them together, and we get the real part, or really twice the real part of z times w bar by our last proposition. And so this is equal to the modulus of z squared plus 2 times the real part of z times w bar. Like I said, that's from combining those two things together. And then we have plus the modulus of w squared. We haven't used an inequality yet, but we're about to. So let's recall that we can exchange this for the absolute value of this and create an inequality. So this is all less than or equal to the modulus of z squared plus 2 times the absolute value of the real part of z times w bar plus the modulus of w squared. So if this real part is positive, we have equality, but if it's negative, we've produced an inequality. Now from here, we want to use an inequality from the last proposition, which exchanges this absolute value of a real part with a modulus. So this is less than or equal to the modulus of z squared plus 2 times the modulus of z times the modulus of w, where I've skipped a very small step in there. Maybe post in the comments if you know what it is. And then plus the modulus of w squared. But notice that factors out nicely to modulus z plus modulus w, quantity squared. But now let's see, looking at the extreme left-hand side, the inequality that we have here, and the extreme right-hand side, we have gotten exactly what we wanted. So I want to finish this video off with a couple of examples and then leave you with some warm-up exercises. Okay, now we're going to look at some examples of sets in the complex plane. So in this first case, we're going to look at the set of all complex numbers z that satisfy the condition the modulus of z is equal to 4. So in other words, this is all complex numbers that are 4 units from the origin. Now you might be able to write down exactly what that is immediately, but let's maybe go through a couple of details just to see that our guess is correct. So let's say z was equal to x plus iy. I've exchanged my a's and b's for x's and y's because these are kind of variable at this point. So now this equation right here is the same thing as the square root of x squared plus y squared equals 4, or x squared plus y squared equals 16. So that means we get something that looks like a circle of radius 4. So this would be this set. So all of the numbers that are 4 units from the origin can be written in a complex plane like this. Okay, so now let's get rid of this and look at a little more interesting of an example. Okay, now let's look at this problem. We want to look for all complex numbers that satisfy the following inequality. We've got 8 is less than or equal to the modulus of 4z minus 12, which is less than or equal to 16. Let's notice everything here is divisible by 4, so we can just divide everything by 4, hopefully simplifying it a little bit. So that'll give us 2 is less than or equal to z minus 3, which is less than or equal to 4. Okay, so that's starting to look good. And now let's set z equal to x plus iy again. Okay, so writing this with this version of z gives us 2 is less than or equal to the modulus of x minus 3 plus iy, which is less than or equal to 4. So something that looks like that. So notice I grouped my 3 with the real part of z. Now I'll square all parts of this just because the modulus of a complex number squared is a little bit nicer to write down than just the modulus. And that will give us a 4 here, a 16 here if we square this. Then, using what we saw was the modulus of a complex number squared on previous boards, that gives us the inequality 4 is less than or equal to x minus 3 squared plus y squared, which is less than or equal to 16. But notice each of the boundaries here is a circle that is centered at 3, 0. Just given the fact that we know the equation of a circle in the real plane, here, this one will be of radius 2, this one will be of radius 4. So the inequality means that we get kind of everything in the middle. Okay, so in other words, we go over here to the point 3, that's our circle. Then we think about our 2 radii, so our inner radius and our outer radius. So our inner radius is right there, and then our outer radius, one more, will be out here. Then draw a circle at each of these spots. So maybe it would be something like this. And then the set we're looking for is everything in the middle there. So it's that annulus. Okay, so I think that looks pretty good. Okay, so let's maybe do one more example, and then I'll leave you with some warm-up exercises. Okay, so let's look at this last example before I give you some warm-up problems. And that's the modulus of z plus the modulus of z minus 1 equals 2. So we're going to do the same thing that we did before, and that is write it kind of in terms of a plane curve in terms of x and y, just to get a feel for it. Later we'll have like a standard way of writing down these shapes using complex numbers. Okay, so anyway, we've got z is equal to x plus iy. So that means we can rewrite this as the modulus of x plus iy plus the modulus of x minus 1 plus iy, just as we did previously. Okay, so where should we go from here? Let's instead write down what these moduluses are just by the definition. So this is going to be the square root of x squared plus y squared here. Here we'll have the square root of x minus 1 squared plus y squared here. And here we'll have the number 2. And now from here what we'll do is square this entire thing to start getting rid of the square roots. So that'll leave us with x squared plus y squared plus 2 times the cross term, which will be x squared plus y squared times this x minus 1 squared plus y squared. Maybe I'll multiply that out so we have x squared minus 2x plus 1 plus y squared. Okay, that's good. and then plus x squared minus 2x plus 1 plus y squared equals 2, where that's this thing multiplied out, just like we had previously. Now let's move everything to one side of the equation so we can start to square and get rid of this. Okay, so that's going to leave us with something that's admittedly a little bit gnarly. So I'll maybe move this to the other side of the equation, move the 2 over. That leaves us with 2x squared plus 2y squared. And then we'll have minus 2x minus 1. We get that minus 1 by subtracting the 2 over, equals negative 2 times the square root of x squared plus y squared times x squared minus 2x plus 1 plus y squared. And now from here, I'll skip a couple of steps, and that's just because they're really not super fun. But what I want to say, what you can end up with after squaring both sides and then collecting terms, is something that looks like x minus 1 squared over something, which I'll call a, plus y squared over something, which I'll call b, is equal to 1. In other words, this is the equation of an ellipse. So maybe as a little warm-up or homework exercise, go from this step to making it look like this, just to convince yourself that this is right. Okay, so now, like I promised, I'll leave you guys with some warm-up exercises. I'd like to give you guys a nice little trick for plotting things in the complex plane using Mathematica. So I'm sure there are a number of ways to do this, but this is a way that I think is fairly straightforward and nice. So the first thing that you'd like to do for notational convenience is to set z equal to x plus I, because we'll be working with the complex variable z here. And let's notice that I is capitalized because all important constants in Mathematica are capitalized. So first off, we'd probably like to find the modulus. So Mathematica uses the function abs, so that's like absolute value for the modulus of a complex number. So if we were to do something like find the modulus of 3 minus 2i, we would expect that to be 9 plus 4, which is 13, and then take the square root, just by what we saw for calculating the modulus. So that's exactly what we get, the square root of 13. And then next, maybe we'd like to find the real part. So the Mathematica function for that is quite easy. It's just RE. So let's look at the same thing. RE of 3 minus 2i. So that should obviously give us the number 3, and it does. Now let's check the imaginary part. So it's aptly named as well, just IM. So the imaginary part of 3 minus 2i is negative 2. Next, we'll need the tool, which is the contour plot. And so this can be used to plot solution sets to equations. So just for a very simple example, let's say we were to plot the solution set to the equation y equals x squared. Then we would just put y equals x squared here. So it's important that you have a double equal sign here to say that it's an equation instead of an assignment. And then furthermore, maybe we take x from negative 2 to 2 and y from negative 4 to 4. Then we'd like to maybe set the axes on. So you would do that here with this axes with the arrow and then true. So if you let this go, you'll see that you get a parabola. So this works out. Okay, so now let's look at some examples, starting with some easy ones and then working towards some ones that would be fairly difficult to plot by hand. So let's say we look at the space in the complex plane where the modulus of z is equal to 3. So in order to plot that, we would do our contour plot, but our equation would now be this absolute value of 3, but that's the modulus of z equals 3. But let's recall that z was x plus I. So this is going to translate this from the complex plane into, well, Mathematica is seeing it as the real plane, but we get the correct plot. And that plot is obviously a circle with radius 3. Now let's look at this next example. So the real part of z plus the imaginary part of z equals 2. So this one is not too tricky to solve by hand. Notice that would just be x plus y equals 2. That's going to be a line with a slope of negative 1. And notice that's what we get if we plot that. Okay, nice. So now let's look at this one, which is a little bit trickier. So here we have the absolute value of the modulus of z minus 1 minus the modulus of z plus 1 equals 1. So I'm careful to say the absolute value on the outside because we've got this modulus on the inside, which turns these into real numbers. Of course, in Mathematica, you use the ABS for modulus and absolute value, so that won't show up down here. Okay, so I've translated this equation into my contour plot, and I'm still good with this viewing rectangle, and we still have the axes on. And notice this gives us a nice hyperbola. So this is something that would take a bit of work to do by hand, but would be possible. Now let's look at this one. Again, this one would be fairly easy to do by hand, but I think it's nice just to see it very quickly. We have the real part of I times z minus 2 equals 1. So I've changed my viewing rectangle a little bit. Notice I have capital I here because it's a constant for Mathematica, and I get a horizontal line, which is to be expected if you write down the equations of what this means carefully. Okay, so let's do one more. So I think this one would be quite tricky to graph by hand, but you could maybe give it a go if you wanted to, and that will be the modulus of z squared plus 1 equals the modulus of z. So here we have that into our equation. It's absolute value, but that's modulus if we have complex numbers. Z squared plus 1 equals modulus of z. I've changed the viewing rectangle a little bit. That's just from trial and error, kind of off the video. So if I push enter on this, notice I get these two. They're not quite circles, but these two bubbles. So I think this is a nice picture. So I'm going to put a link to this notebook in the description, and if you guys are psyched, you can look at some more examples. Maybe if you find some particularly nice examples, put them in the comments. Okay, so here's some nice problems that would maybe warm you up to work on some harder exercises based off of this stuff. So the first of which is to fill in the details for anything we skipped. So that would be like the last example or the two portions of that proposition. Next, describe the points in the complex plane satisfying these three equations. So we've got modulus z minus I plus modulus z plus I equals 3. We've got the modulus of z is equal to the absolute value of the real part plus the absolute value of the imaginary part. And finally, we have the absolute value of the modulus of z minus 1 minus the modulus of z plus 1 equals 4. So I think you'll have a good feel for how all of this works after these types of warm-ups. And that's a good place to stop.